Hello viewers, in the last session we have seen that power series are analytic okay, and also that their differentiation is obtained by differentiating the terms of the power series and then summing up. Okay. So, if f of z, so recall that if f of z is equal to sigma C n z power n, power series of type 1, n equals 0 through infinity. Okay. Then for mod z strictly less than r, here we will assume r is strictly positive. Okay. Then we saw that then f is analytic on B 0 r, and f prime of z has the form n equals 0 through infinity. Okay. N C n. So, n equals 1 through infinity, I apologize, equals 1 through infinity n C n z power n minus 1 for r, for mod z less than r. Okay. So, the differentiation of the power series is differentiating it term by term and then summing up within the radius of convergence. Okay. So, that we have seen last time. Okay. So, as an example, we will see the following. If we consider the power series f of z equals z power n by n factorial, sigma n equals 0 through infinity, then we will show that this is the power series expansion for the exponential function e raised to z. Okay. So, firstly there is one note. Okay. So, within this example itself I will make that note. There is a little ambiguity here. So, when we write f of z, so when we write f of z equals sigma n equals 0 through infinity C n z power n for type 1 series, then what we really mean is that this is f of z. Okay. So, for type 1 series, this is a split function, f of z is equal to C 0 when z equals 0, and f of z is that series when z is not equal to 0. Okay. Since 0 power 0 is not defined, we split the definition of f of z. Okay. Note for type 2 series that f of z is defined to be C 0 when z equals a for type 2 series, and f of z is sigma C n z minus a power n when z is not equal to a. Okay. One needs to make the distinction because at z equals 0 and n equals 0, you have the ambiguity of 0 raised to 0, and 0 raised to 0 is not defined. Okay. 0 power 0 is not defined. So, there is that split form, and then so having made that note, let us look at this series. This series has the property that firstly the radius of convergence of f is, okay, by simple ratio test calculation. Okay, by ratio test, the radius of convergence of f is infinity. Okay, or you can use the Cauchy-Hadamard formula, either way one can get this. Okay. So, so we can differentiate this power series. Okay. So, f prime of z for the same radius of convergence will look like n equals 1 through infinity of the differentiation of z power n is n z power n minus 1 divided by n factorial. Okay. So, I will cancel the n in the numerator and the denominator. So, I will cancel the n in the n factorial to get n equals 1 through infinity z power n minus 1 divided by n minus 1 factorial. And by readjusting the index once again, this is nothing but n equals 0 through infinity z power n by n factorial, which is your f of z to begin with. Okay. So, we have shown that f prime of z is nothing but f of z for mod z, okay, or for any z belongs to R, or not R, I apologize, C, okay, because the radius of convergence is infinite. Okay. Not only that, observe that f of 0 is 0, or rather 1. F of 0 should actually equal 1, because C 0, okay, since C 0 for this series, since C 0 for this series is 0, is 1 rather, 1 by 0 factorial, okay, which is 0 factorial is defined to be 1. So, you have 1. Okay. F of z, f prime of z is equal to f of z. Okay. So, so f, so the given power series is a solution to the initial value problem f prime of z equals f of z and f of 0 is equal to 1. Okay. So, since we know that okay, or by the existence and uniqueness of solutions to differential equations, okay, we know that the solution to this IVP has to be unique. Okay. So, so we know that e power z is also a solution. We defined the solution to this IVP as e power z. Okay. So, the e power z has to equal this power series sigma z power n by n factorial, n equals 0 through infinity. At z equals 0, we define this to be 1. Okay. So, e power z is this power series, has this power series expansion around z equals 0. Okay. For this is for any z belongs to C, for z belongs to C, z not equal to 0. Okay. So, I will split this, this is equal to 1 if z is equal to 0. So, that is the power series expansion of e power z, and it is valid all throughout the complex plane. All right. So, we see that e power z has a power series expansion for any complex number, okay, modulo this small change at z equals 0. Okay. So, now a question can be as follows: is every analytic function a power series, or so to say, is can every analytic function be expressed as a power series? Well, we already know that the answer cannot be yes, or we know that the answer is no, because 1 by 1 minus z is analytic on. Okay. So, let me write the question. Question is every analytic function a power series on its domain of analyticity. That is the question. Okay. So, we know that 1 by 1 minus z is analytic on all of C except at one point, namely 1. So, on C minus 1, on the set C minus 1, 1 by 1 minus z is analytic, but 1 by 1 minus z is equal to one kind of power series, which is the geometric series z power n equals 0 through infinity for only for mod z less than 1. Okay. Beyond mod z less than 1, we know that we know at least that this power series is not correct for 1 by 1 minus z. Okay. So, 1 by 1 minus z does not equal this power series for mod z less than 1, mod z greater than 1, sorry. Okay. So, so the point is not all analytic functions are equal to a unique power series on the whole domain of of their analyticity. Okay. So that happens. So then one can ask the following modified question: is every analytic function equal to some power series, okay, if not on all of the domain of analyticity, at least in a small neighborhood around a point of analyticity. Okay. So, is every analytic function equal to some power series locally, i.e. in some B A R for R positive, okay, where A is a point of analyticity for f for the given function. Okay, that is what locally means. Locally means that there is a small disk around the point of analyticity, okay, of radius of positive radius, such that a certain property holds. That is a local property, and the property we are interested in here is whether every analytic function is locally an analytic a power series rather. Okay. So, the answer to this question turns out to be yes, and this is answered by the Taylor's theorem. The Taylor's theorem tells us that every analytic function is locally a power series. Okay. So, let us see what the Taylor's theorem says. Okay. So, here is the statement of Taylor's theorem. Okay. So, let f be an analytic function on B A R. Okay. So, since we are interested in expressing the analytic function as power series locally, okay, although f could be analytic on a bigger set, we will only assume for the time being that it is analytic on the disk itself, okay, B A R. Then there exist unique constants C n such that C n, I should say n belongs to integers n greater than or equal to 0. Okay, n belongs to integers and n greater than or equal to 0. Okay. There exists unique constants C n such that f of z is equal to sigma n equals 0 through infinity C n z minus a power n, z belongs to B A R for any z belongs to B A R. Okay. F of z equals that power series on that disk. Okay. The constant C n furthermore, okay, so the constants C n are given by C n is equal to the nth derivative of the function f at a divided by n factorial, which is actually equal to 1 by 2 pi I the integration over C r. Okay, I will explain what C r is. It is a circle of radius little r, okay, around a of f of w by w minus a raised to n plus 1 d w, where C r is a circle of radius r. Okay, radius r strictly less than capital R. Okay, so I will say 0 strictly less than little r less than capital R. Okay, oriented, okay, centered at A and oriented in the counterclockwise direction. Okay, in the counterclockwise direction. That is the positive direction, recall. So, firstly note that by what we have noted earlier, okay, by the theorems earlier, we know that every analytic function is differentiable any number of times. So, the nth derivative of an analytic function f exists, okay, in its domain of analyticity. So, this expression here f n, the nth derivative of f at the point A is valid, okay, makes sense. Okay. And by Cauchy's integral formula for the nth derivatives, we know that the nth derivative of f at A divided by n factorial is precisely the expression on the right hand side. So, that is the statement of the Taylor's theorem. Okay. So, it not only tells us that that an analytic function is locally expressible as power series, but also that the constants C n in the power series are given by the nth derivative of f at A divided by n factorial. So, in order to prove this theorem, we will prove this theorem, but in order to prove this, we first need a couple of lemmas. Okay. So, here is the first lemma. Okay, lemma. So, I am following the development here from one of the textbooks, Introduction to Complex Analysis by Priestley. Okay. So, lemma 1, since I did not define what uniform convergence is, I will have to I will need a result which will tell me when I can exchange integration and summation. Okay. So, here is lemma 1, let gamma be a path and let u, u naught, u 1, etc. Okay. So, any u n for that matter, n belongs to non-negative integers. Okay. So, u be continuous on the trace of gamma in the complex plane, okay, and assume that sigma k equals 0 through infinity of u k of z, okay, converges to u of z, which is pointwise convergence, okay, for all z belongs to gamma star, the trace of gamma in the complex plane. Now, assume that there exist constants m k, okay, k belongs to non-negative integers, okay, k belongs to z, k greater than or equal to 0, okay, such that sigma m k, okay, k equals 0 through infinity converges, and this m k's are related to u k's as follows: u k of z, okay, in modulus is less than or equal to m k for all z belongs to the trace of gamma. Okay. So, for any z belongs to the trace of gamma, the modulus of u k of z is less than or equal to m k. Okay. Then Okay, then sigma, then the conclusion is sigma k equals 0 through infinity of the integration, contour integration of u k of z over the contour gamma, okay, is equal to the integration over the contour gamma of the summation of u k of z dz k equals 0 through infinity. So, we can exchange the integration and the summation. Okay. So, this is equal to the integral over gamma of u of z dz by definition of the summation. Okay. Since the summation converges to u of z, I am just replacing the summation by capital U of z. Okay. So, we know that from our experience with functions of real numbers and series of real functions, we know that it is not necessary that we can always exchange the integration and summation. Okay. So, under these circumstances, this lemma gives us a sufficient condition under which we can exchange the integration and summation. Okay. Recall that the summation involves a limiting process. Okay. And if it were a finite process, if you are taking finite sums, you can always exchange the integration and summation, because integration is a linear operator. Okay. So, but when you have infinite sums, you have to be more careful. There is a limiting process, and it does not commute very well always with integration process. Okay. So, this lemma tells us that if you have a convergent series of functions, okay, a term by term convergent series of or point by point convergent series of functions. So, for each point z, this series of functions converges to u of z, okay, and at least for all z belongs to gamma star. Okay. And if these u k of z in modulus are less than or equal to some fixed constants m k, okay, and sigma m k converges, then you can exchange the integration and summation for this u k of z, okay, over the contour gamma. Okay, that is the content of this lemma. Okay. So, here is the proof. So, first we will take finite sums of this u k of z. So, for n equals 0, 1, etcetera, for any non-negative capital N, let u n of z, capital U subscript n of z, be the finite sum sigma k equals 0 through capital N of u k of z, little u k of z. Okay. So, both u n, capital U n and capital U are continuous. Of course, capital U n is continuous because it is a sum, finite sum of continuous functions, okay, and capital U is given to be continuous, it is continuous by hypothesis. Okay. So, capital U are continuous where and hence integrable on gamma star. On the set gamma star in the complex plane. So, now also we know that sigma modulus of u k of z, okay, converges by comparison test. That is clear, because sigma m k converges. So, the hypothesis of the lemma says sigma m k converges, and term by term modulus of u k of z is less than or equal to m k. So, definitely sigma u k converges okay, for any z, okay, by comparison test for any z belongs to gamma star. Okay. So, now what we will do is we will estimate u of z using the u capital N of z. Okay. So, what we will do is we will take the difference of u of z, okay, with u k of z, but what we will do is we will take the difference of the integrals of these. Okay. So, and estimate them. So, the contour integration of u of z dz over gamma minus the sum from k equals 0 to capital N of the integration the contour integration of u k of z dz over gamma, okay, in absolute value in the modulus. This is nothing but the modulus of the contour integration of u of z minus u capital N of z dz. Right, one and the same. You can exchange the integration and summation here, because you have a finite sum here, k equals 0 through n. Okay. So, this is less than or equal to, okay, this is less than or equal to, by one of the estimations we had on integration. This is less than or equal to the supremum over z belongs to gamma star of the modulus of the integrand u of z minus u n of z, okay, times the length of gamma, okay, the length of gamma star rather, okay, in complex plane, the length of the contour gamma. So, I will just say gamma. Okay. So, this is less than or equal to, in turn this is less than or equal to, well, the difference u of z minus u n of z, okay, is equal to the tail of the series sigma u k of z. Okay. So, this is less than or equal to the supremum over z belongs to gamma star of the modulus of the tail, okay, and which in turn is by an infinite version of triangle inequality is less than or equal to k equals n plus 1 through infinity. This is the tail of the absolute value series of u k of z. Okay. So, I am using an infinite version of the triangle inequality here. Okay. So, then we get that the earlier is less than or equal to. So, this is actually equal to, notice that this thing within the absolute value or the modulus is equal to this tail k equals n plus 1 through infinity, sigma k equals n plus 1 through infinity of u k of z. Okay. And then you shift the absolute value inside like this, okay, by triangle inequality, okay, and then you get this times the length of gamma. Okay. So, then this is in turn less than or equal to the supremum, well, each of these u k of z in modulus we know is less than or equal to m k by hypothesis. So, this is less than or equal to sigma k equals n plus 1 through infinity of m k times the length of gamma. Okay. And as n goes to infinity, since m k sigma m k converges, as n goes to infinity sigma k equals n plus 1 through infinity m k tends to 0, okay, since sigma m k converges. Right. If you have k equals 0 through infinity converges. Okay. If you have a convergent series, okay, the tail of the series we know tends to 0. Okay. So, this allows us to say that, so this estimate which we started off with as limit as n goes to infinity, okay, will be tending to 0, okay, will be tending to 0. So, the integration of u of z, the contour integration of u of z dz, okay, is equal to okay. So, we have in modulus this is equal to 0. So, this is equal to sigma k equals 0 through infinity, okay, limit as capital N goes to infinity. So, we have infinity on the top of the summation, as the top bound of summation of the contour integral of u k of z dz. Okay. So, this I e okay, gamma sigma u k of z dz, because that is what capital U of z is, k equals 0 through infinity. This is equal to sigma k equals 0 through infinity integral gamma integral over gamma of u k of z dz. Okay. Or in short, we can exchange the summation and integration under these circumstances. Okay. So, it is the end of proof of this lemma, and we will use this for the proof of Taylor's theorem. Okay. So, this is the first result that we will need, okay. And the next result that we will need to prove Taylor's theorem is as follows. So, this is about the coefficients of power series. Okay. So, let f of z equals sigma k equals 0 through infinity c k z power k, where the power series, where this power series has radius of convergence r strictly greater than 0. So, positive radius of convergence. Okay. Then we know that capital little f is analytic. Okay. So, so it is differentiable term by term, or I mean its differentiation is the differentiation of these terms, okay, and then summing it up. Okay. So, there is also the fact that then the coefficients of this power series C n, okay, are given by 1 by 2 pi I integration over C r f of z by z power n plus 1 d z, where 0 less than or equal to r strictly less than r, n greater than or equal to 0, okay, and C r. Okay. So, I will write below and C r. There is a clash of notation, maybe this is little c n and this is capital C r. Okay. So, and capital C r is a circle of radius r, is the contour, okay, a circle of radius r centered at 0, okay, and oriented positively. So, this tells us that if you take a power series which has positive radius of convergence, okay, then its coefficients or then its constants are unique, and there is a specific formula for that constant. Okay, and the constants are given by C n equals 1 by 2 pi I, the contour integration of f of z divided by z power n plus 1 over the contour C r, where r is C r is a circle of radius little r strictly less than the radius of convergence, okay, and it is oriented positively. Okay. So, let us see the proof of this theorem, of this little lemma, okay, and it goes as follows. The integration of f of z by z power n plus 1, okay, the contour integration over C r of f of z divided by z power n plus 1 d z, okay, this is equal to the integration over C r of clearly sigma k equals 0 through infinity of C k of z power k divided by z power n plus 1 d z. Okay. And this in turn is the integration, okay, of C r, okay, sigma k equals 0 through infinity of C k. I will divide z power n plus 1 term by term. So, I will get z power k minus n minus 1 dz, okay, and then all this dz, okay. And provided I can interchange the limit or sorry, the summation and the integration. Okay. So, I get sigma k equals. So, let us for the time being assume that I can interchange them. I will show that I can interchange them by the earlier result. Okay. So, then this is equal to sigma k equals 0 through infinity of the integration contour integration over C r of C k z power k minus n minus 1 dz. Okay. C k's are constants. So, this is equal to 2 pi I. Okay. So, there is only one survivor for this integral as k runs from 0 through infinity. Okay. When k equals n, you have this integration for a small enough r. This integration is actually equal to 2 pi I times C n. Okay. So, this will give you 2 pi I times C n when because of the survivor z power minus 1 when k equals n. The other functions z power k minus n minus 1 for k not equal to n give 0 upon integration by the fundamental integral that we calculated earlier. Since C r is a simple closed curve, the integration upon C r of these functions give us 0. Okay. So, this is 2 pi I times C n, and I should just now justify how I can exchange the integration and summation. Okay. So, oh, by the way, this tells me that C n is actually equal to, so C n is equal to 1 by 2 pi I times the integration of f of z divided by z power n plus 1 over circle of radius r. So, firstly notice that if I set let u k of z equals C k z power k minus n minus 1, okay, and capital U of z is z power minus n minus 1 f of z. Okay. So, then I know that then U of z is equal to sigma k equals 0 through infinity u k of z on at least z belongs to C r star. It is actually true on all of the for all z belongs to the disk of convergence. Okay. So, but at least it is true on the trace of C r. Okay. Also, the modulus of u k of z and all these functions are continuous. Okay. And this is clear because that is what f of z is. Okay. So, this is clear, and these functions are continuous. U k of z is equal to m k. Okay. What is m k? This is modulus of C k r power k minus n minus 1. That is the constant we are looking at. Okay. And sigma m k converges, because little r is strictly less than capital R, which is the radius of convergence. So, this shows that the hypotheses of the previous lemma are satisfied. Okay. So, all the hypotheses are met. You have u k converging to sigma u k converging to u of z, okay, and then u and u k's are all continuous. Further, you also have that this modulus of u k of z is less than or equal to m k. Actually, it is equal to this m k, and sigma m k converges. Okay. So, you can exchange the limit the summation and the integration, and so so you have this formula for C n's, the coefficients C n's in the power series. So, that completes the proof of this second lemma. Okay. And now, we are ready to prove the Taylor's theorem. Okay. So, we will start by fixing let me revisit the statement of the theorem. Okay. So, it says that a function f is assumed to be analytic on BAR, R positive. Okay. Then f is locally a power series, and the constants C n are given by moreover the constants C n are given by the nth derivative of f at a divided by n factorial. Okay. So, there are several things to prove here. So, firstly, you fix a certain z belongs to BAR. Okay. What we have to show is that the power series actually converges to f of z. Okay. We have to show two functions are equal. So, for z belongs to BAR, we have to show that the values of the functions are equal. Okay. So, fix some z and choose r little r such that the modulus of z minus a is less than little r is less than capital R. Okay. So, we want a little r between modulus of z minus a and capital R. Now, by Cauchy's integral formula, we know that f of z, the function f of z. Okay. Remember, we are trying to reconcile the power series, the value of the power series and the value of f of z. Okay. So, let me first look at the value of f at z. This is 1 by 2 pi I times the integration over CR, the contour integration over the contour CR of f of w divided by w minus z dw. Okay. So, that much I know from Cauchy's integral formula. Okay. Now, since modulus of z minus a is less than modulus of w minus a for all w belongs to the circle of radius r centered at a. Okay. So, since z minus a, notice, is strictly less than r. Okay. So, what you can do is you can take 1 by w minus z, which appears here in the integration. So, in the integration, the integrand is f of w divided by w minus z. I will concentrate on the denominator, or namely I will concentrate on 1 divided by w minus z. I will multiply f of w later. Okay. So, 1 divided by w minus z can be written as 1 by w minus a times 1 by, this is a standard trick, we will write this as 1 minus z minus a by w minus a. Okay. And since modulus of z minus a is less than modulus of w minus a, we can expand this piece within the square parentheses, we can expand that as geometric series. Okay. I will write that 1 by 1 minus z minus a by w minus a can be expanded as geometric series. Okay. So, 1 by w minus z, this expression here is equal to 1 by w minus a times that geometric series, which is sigma. Okay. So, sigma n equals 0 through infinity of z minus a by w minus a whole raised to n, or z minus a power n divided by w minus a power n. Okay. So, that much I can do. Okay. So, I have somehow got a power series within the value for f of z. Okay. So, now I will try to express f of z as power series itself. Okay. So, f of z from that Cauchy's integral formula, I will say from star, this is star. Okay. From star, did I use star earlier? Okay. From star, or let me call it star star, maybe I have used star. Okay. So, star star. From star star, f of z is equal to 1 by 2 pi I times integration over the contour C r of f of w divided by w minus z d w, and I have written w minus z in this fashion here. Okay. So, this is equal to 1 by 2 pi I integration over C r of f of w, I will keep the f of w aside, okay, times 1 by w minus a times the sigma n equals 0 through infinity of z minus a raised to n divided by w minus a raised to n, and then all this dw. On the compact set C r, the trace of C r, okay, the continuous function f of w, okay, f is bounded. It is actually analytic. So, it is definitely continuous and it is bounded. Okay. So, there is an m, okay, such that modulus of z minus a power n, okay, divided by modulus of z minus a power n divided by w minus a power n plus 1 f of w is less than or equal to m divided by r. So, for this f of w I am using m, and then w minus a in modulus is equal to r, okay, and then I will have I took 1 r for modulus of w minus a, 1 modulus of w minus a, and then I take n r raised to n for the remaining n, okay, and then I have modulus of z minus a raised to n. Okay. So, let me call this constant as, so since we have fixed z, all of the right hand side here is a constant, let me call that m n. Okay. The series sigma m n converges, because what we have is a constant, okay, is a constant times a geometric series. When we sum up sigma m n, okay, we have a constant times a geometric series, okay, and that converges. Okay. So, now by lemma 1, therefore, okay, we have sigma m n converges, okay, and this thing is less than or equal to m n, okay, for all n, okay, and so in here I can exchange the integration and summation. Okay. So, by lemma 1 what I have is by lemma 1 f of z is actually equal to sigma n equals 0 through infinity 1 by 2 pi I times the integration over C r of f of w by w minus a raised to n plus 1 dw, okay, times z minus a raised to n. Okay. So, I will put this within parentheses times z minus a power n, and everything is in sigma, Okay. And this much from Cauchy's integral formula, we recognize that to be the nth derivative of f at a divided by n factorial. Okay. So, by this is equal to this by Cauchy's integral formula for higher derivatives. Okay. So, we proved all our assertions, and that proves Taylor's theorem. Okay. So, we will see some examples in the next session. I will stop here.